Hello, everyone. Let me just change to full screen. I just need to set up a few things. Hello, everyone. Let me just change to full screen. I just need to set up a few things. I'm going to be learning calculus this stream. It's been quite some time. I finished calculus 2 I just need to last time. Hold on. And the last topic I learned was about conic sections. The first chapter in Calculus 3 seems to be about vectors, so that's what I will be studying. Okay, let me just change to full screen. Okay, so I'm going to be using the same book, OpenStax. This time I'm going to be starting with volume 3. The last chapter of volume 2 was this, parametric equation on polar coordinates. Yeah, and the last thing I learned was about conic sections. So this time I'm gonna be, let's see what the chapters are. Vectors, differentiation of functions of several variables, multiple integration, vector calculus, and second order differential equation. Okay, let's start with the, no, not this, it's the other one. Introduction, vectors in space. I've already learned about vectors before, but I need a lot of revision on this. Just to accept modern astronomical observatories often consist of large number of parabolic reflectors connected by computers used to analyze radio waves. Each disk focuses the incoming parallel beams of radio waves to a precise focal point. This is a parabola shape. So I think any ray coming directly over here gets reflected onto the focus. If the surface of one of the parabolic reflectors is described by the equation this, where is the focal point of the reflector? We are now about to begin a new part of calculus course when we study functions of two or three independent variables in a multidimensional space. Maybe the computations are similar to those in the study of single variable functions, but there are also a lot of differences. In the first chapter, we examine coordinate systems for working in three-dimensional space along with vectors, which are key mathematical tools for dealing with quantities in more than one dimension. Okay, vectors in a plane. A vector is a quantity that has both magnitude and direction. A vector, should I zoom in? A vector, wait. Never mind. A vector in a plane is represented by a directed line segment, an arrow. The endpoints of the segments are called the initial point and the terminal point of the vector. An arrow from the initial point to the terminal point indicates the direction of the vector. The length of the line segment represents the magnitude. Use this notation to denote the magnitude of the vector v. A vector with an initial point and terminal point that are the same is called the zero vector, denoted 0. The zero vector is the only vector without the direction, and by convention can be considered to have any direction convenient to the problem at hand. Vectors with the same magnitude and direction are called equivalent vectors. We treat equivalent vectors as equal even if they have different initial points. Thus, if v and w are equivalent, we write this. So they just need the same direction and magnitude, and the position is not relevant. The use of boldface lowercase letters to name vectors is a common representation in print, but there are alternative notations. When writing the name of a vector by hand, for example, it is easy to sketch an arrow over the variable than to simulate boldface type. So arrow v. When a vector has an initial point p and a terminal point q, the notation pq is useful because it indicates the direction and location of the vector. So sketch a vector in the plane from the initial point p11 to the terminal point 85. Uh, 1 and 85, this are right. Hold on, is there any screenshot? Extension, not favorite. Uh, Control Shift S. Oh, copy. And then in Excalibur, draw, I can just paste it. Or if anyone knows like if I can draw directly in Desmos, it would be helpful. So let's use blue. So I can draw from point 1 1, not here. Here is 1 1. And then they said 8 5, right? 8 5 8. It would be somewhere here. So it will look like this. Bam. Vectors have many real-life applications, including situations involving force or velocity. For example, consider the force acting on a boat crossing a river. The boat's motor generates a force in one direction, and the current of the river generates a force in another direction. Both forces are vectors. We must take both the magnitude and direction of each force into account if you want to know where the boat will go. A second example that involves vectors in a quarterback throwing a football. Okay, I get it. A real number is often called a scalar in mathematics and physics. Unlike vectors, scalars are generally considered to have magnitude only but no direction. Multiplying a vector by a scalar changes the vector's magnitude. This is called scalar multiplication. Note that changing the magnitude of a vector does not indicate a change in its direction. Okay, so this is v. And then if we multiply it by a scalar, for example 2, now we get 2v. The direction remains the same, but the magnitude increases. The product kv of a vector v and a scalar k is a vector of magnitude that is k times the magnitude of v. Oh yeah, and minus v would be the other direction. I think a negative in that direction, it's like that direction, with a direction that is the same as the direction of v if k is greater than 0, and opposite the direction of v if k is less than 0. This is called scalar multiplication. Another operation we can perform on vectors is add them together in vector addition, but because each vector may have its own direction, the process is different from adding two numbers. The most common graphical method for adding two vectors is to place the initial point of the two vectors at the terminal point of the first, figure 2.5a. Also, they're adding v and w. So they are placing the initial point of w at the terminal point of v and going from this direction to this direction is the same as going this direction. And this is how we represent the sum of vectors. To see why this makes sense, suppose, for example, both vectors represent displacement. If an object moves from the initial point to the terminal point of vector v, then from the initial point to the terminal point of vector w, the overall displacement is the same as if the object had made just one movement from the initial point to the terminal point of the vector v plus w. The second method for adding vectors is called the parallelogram method. Yeah, I guess it's this. I think you're placing both the initial points at one point, and then you're making a parallelogram or a rectangle. With this method, we place the two vectors so they have the same initial point. Then we draw a parallelogram with the vectors as two adjacent sides. Yeah, I get the gist of it. It is also appropriate here to discuss vector subtraction. This is v, and then minus w would be the opposite direction, right? So v plus minus w would give this. It is also appropriate here to discuss vector subtraction. We define v minus w as v plus minus w. It follows from the length of one side is less than the sum of the length of the remaining sides. So we have v plus w is less than or equal to the magnitude of v plus w is less than or equal to magnitude of v plus magnitude of w. This is called the triangle inequality. So we need to sketch vectors. Yeah, we write this. Hold on. You have v, and then you have actually no. Then you have w, stroke width, stroke size, sloppiness. Right. So they're asking 3w. So basically this would be extended 3 times. But I don't know if it would fit. Imagine one vector going from here all the way till there. Then v plus w. So we have v this is v, the green one is w, so this is v plus w, and then 2v minus w, and then 2v. Let's put this here. Let's put this here. Is there a way to flip this? To v minus w. The resulting vector is this 2v, that minus w. Vector components. Working with vectors in a plane is easier when we are working in a coordinate system. When the initial points and terminal points of vectors are given in a Cartesian coordinates, computations become straightforward. V has initial points 3, 2 and the terminal points 7, 2 are these two equivalent vectors. So V has initial point 3, 2. initial point 3, 2, and then 7, 2. Wait, there's a way of figuring it out. Can I draw on the thing? Not here. Is there a way to draw on the web page? So I thought Microsoft Edge had one of those. Anyways, so comparing vectors, I think a simple way of doing this is checking the difference. So the difference in x is 4, difference in y is 0. So it's like from 3 to 7 2, it's like this. Just choose blue. The vector is like this. W has initial points 1, -4, and terminal point 1, 0. So 1, okay, I can't write here. X is 1, -4, and 1. No, it's not, because then it's a vector that's going straight up. So 1, -4, it's like going all the way here. Then 1, 0. So since they have a different direction, they are not the same vectors. They are not equivalent vectors. 0, 0 to 1, 1. Let's see. 0, 0 to 1, 1. -2, 2 to -1, 3. Okay, I can't. -1, -2, -2, 2 to -1, 3. -1, 3. Oh, yeah, I think it's the same. Because the difference in x for both of them would be 1. The difference in y would be 1. Yeah, so the direction and magnitude would be same. Yeah. So over here, which of the following vectors are equivalent? A and B and E, since there's a difference of 1 in the x and difference of 2 in the y. And that's it, I think. Yeah. We may have seen how to plot a vector when we are given an initial point and a terminal point. However, because a vector can be placed anywhere in the plane, it may be easier to perform calculations with a vector when its initial point coincides with the origin. Should I? How does dark mode look like? OpenStax.org. Wait. Why is it not working? Hold on. Okay, I don't like it. I'm reverting the change. Okay. Um, Hold on. What happened? I'm reloading the page. Okay, it's stuck in the loading part. We have seen how to plot a vector when we are given an initial and a terminal point. However, because a vector can be placed anywhere in the plane, it may be easier to perform calculations with a vector when its initial point coincides with the origin. We call a vector with its initial point at the origin a standard position vector. Because the initial point of any vector in standard position is known to be 0, 0, we can describe the vector by looking at the coordinates of its terminal point. Thus, if vector v has its initial point at the origin and its terminal point at xy, we can write the vector in component form as v is equal to xy. When a vector is written in component form like this, the scalars x and y are called the components of v. Let V be a vector with initial point x1, y1 and terminal point xt, yt. We can express V in component form as xt minus xi and yt minus yi. To find the magnitude of a vector, we calculate the distance between its initial point and its terminal point. The magnitude of vector vxy is denoted like this or like this, and can be computed using this formula. It's just the Pythagorean theorem. Okay. Let V be a vector with initial point 2, 5 and terminal point 8, 13, and let W equal to minus 2, 4. Express V in component form and find magnitude of V. Then using algebra, find all this. Okay, Control Shift S. Yeah. How do I copy and close? Did it not get copied? Control Shift S. What's happening? Capture area. Copy. Copied. Then I don't understand what's happening. Anyways, it's going from so V be the vector from with initial point 25 and terminal point 813. So V initial is at 25, and then the terminal is at 813. So then V is 13 minus 5. Nope. 8 minus 2. Like at the origin, it would be like this. So it's basically 6 and 8. And then W, I think it's better if I write it like that. W is minus 2, 4. Express V in component point and find the magnitude. So the magnitude of V is 6 square plus 8 square. Six square plus 8 square is 10. Okay. V plus W. I'll bring that guy back. This is, you just need to add the X component. So 4, then 8 plus 4 is 12. 3V, we multiply these by 3. Then V minus 2W. V minus 2W is 6 minus 4. Then 8 minus 8. 2 and 0. Let's see if we got this correct. So the magnitude is 10. So they got 4 and 12. Yeah. V minus 2W. Oh, it's minus 2W. 6 minus minus 4. This is plus 4. So it's 12 actually. Nope, not 12. I mean 10. So I think it's the picture that's making it slow. Now that we have established the basic rule of vector arithmetic, we can state the properties of vector operations. We will prove two of these properties. The other can be proved in a similar manner. So V plus U, commutative, associative, additive identity is this, additive inverse property, associativity or scalar multiplication. So R and S are both scalars. Distributive property. This is also distributive property. Identity and zero property. Okay. Find the component form of a vector using trigonometry. Find the component form of a vector with magnitude 4 that forms an angle of minus 45 degrees with the x-axis. So minus 45 degrees here. So the y component would be 4 sine theta and the x component would be 4 cos theta, 4 cos minus 45. And the y component would be 4 sine minus 45. Yeah, x is 4 cos minus 45 and then y is 4 sine minus 45. A unit vector is a vector with magnitude 1. For any non-zero vector, we can use scalar multiplication to find the unit vector u that has the same direction as v. To do this, we multiply the vector by the reciprocal of its magnitude. So u, okay. Recall that when we define scalar multiplication, we noted that kv is same as k times v. For u, it follows that magnitude of u is 1. We say that u is a unit vector in direction of v. Is there something like Desmos but for vectors? So finding a unit vector, let v be 1, 2. So v goes from 1, 2 and find a vector w with the same direction as v such that magnitude of w is equal to 7. Hold on, let me think about this. You find the unit vector and then you multiply it by 7, right? So v is and then u is 1 over root 1 plus 2 squared, which is 4. Same thing here. This is the unit vector in the same direction. But then we just multiplied by 7, so we get 7 over root 5 and then 14 over root 5. Yeah. We have seen how convenient it can be to write a vector in component form. Sometimes though it is more convenient to write a vector as a sum of horizontal vector and a vertical vector. To make this easier, let's look at standard unit vectors. The standard unit vectors are I and j. So I is one direction in the x and j is one direction in the y. By applying the properties of vectors, it is possible to express any vectors in terms of I and j in what we call a linear combination. So v is x and y, which can be written as x0, this vector, plus this vector, which can be written as I times the magnitude x plus j times the magnitude y. So vector v can be written like I x and then yj. Express the vector w in terms of standard unit vectors. It will just be 3i plus minus 4j. Vector u is a unit vector that forms an angle of 60 degrees with a positive x-axis. Use standard unit unit vectors to describe u. So u is forms a, so let's say we have v. No, wait, we can just do it with u. U is 60 degrees, x is cos 60, and then y is sine 60. And then we can just write this as cos 60 is half using a calculator. So half I, guess it with root 3 over 2 j. That's the unit vector. Yep. Application of vectors. Finding resultant force. Jane's car is stuck in the mud. Lisa and Jet come along in a truck to help pull her out. They attach one end of the tow strap to the front of the car. Okay. And the other end of the truck's trailer hitch. And the truck starts to pull. Meanwhile, Jane and Jet get behind the car and push. The truck generates a horizontal force of 300 pounds on the car. Jane and Jet are pushing at a slight upward angle and generate a force of 100 pounds on the car. These forces can be represented by vectors as shown in figure 2.21. The angle between these vectors is 15 degrees. Find the resultant vector force, give its magnitude to the nearest tenth of the pound and its direction angle from the positive x-axis. So we just need to do 150 times cos 50, basically this. I've never heard like force being represented in pounds. Cos 15. Okay, I'm using a calculator. They said nearest tenth, right? Yeah. 144.8889. And if we add this with like that's the force in this direction. If we add this with 300, we get 444.89 pounds. Um, 150 cos 15. Find the resultant force, the vector sum, and give its magnitude to the nearest tenth of a pound and its direction angle from the positive x-axis. Oh, wait a minute. I think I found the resultant force just in the positive x direction. So wait. What I'm supposed to do is we have 150 pound and 300 pounds going straight. I'm supposed to find this. So what do we know so far? That this angle is 15. This angle is x. So we have, and then the vector is 150. £150, 300 pounds. Now what? Let's call this V W. So V is actually 150 cos 15 in the I direction, and then 150 sine 15 in the x direction, in the y direction, the upward direction, and then W is just 300 in the I direction. And then what? Oh, wait a minute. V plus W gives us 150 cos 15. All this plus it with 300 in the I direction. Sine 15 in the J direction. Now, if I use a calculator, cos 15 plus 300, I need to be in, this needs to be in degrees. Got 444.888. I plus it with 150 sine 15. 38.823. So we have this total, right? Then I guess we can do like this to find the magnitude. Which is root this square plus this square. If I square, square, plus then I get 446.56. 46.56. What about the direction? So we have these two components, right? We can just do inverse tan of them. So is this right? 4.98. Got this. We got this. Yeah, around 5 degrees. Yeah, this is correct. Let's just go to the next chapter. I'll just do this chapter and then I will end the stream. Vectors in 3 dimensions. A three-dimensional rectangular coordinate system consists of 3 perpendicular axes, the x-axis, the y-axis, and the z-axis, and an origin at the point of intersection, 0 because of the axis. Because each axis is a number line representing all real numbers in R, the three-dimensional system is often denoted by R cubed. The positive z-axis is shown above the plane containing the x and y-axis. The positive x-axis appears to the left and the positive y-axis appears to the right. Now, the question is to ask, how was the arrangement determined that the system displayed follows the right-hand rule? So what's the right-hand rule? We take out our right hand and align the fingers with the positive x-axis. I think the fingers are supposed to be open here. So the fingers are pointing at the positive x-axis. I think the palm is supposed to be facing the... then curl the fingers so they point in the direction of the positive y-axis and our thumb points in the direction of the positive z-axis. Okay. I've seen like a right hand rule in physics. You have the finger, thumb, and the middle finger in like perpendicular directions. In 2 dimensions, we describe a point in the plane with coordinates xy. Each coordinate describe how the point aligns with the corresponding axis. In 3 dimensions, a new coordinate c is appended to indicate alignment with the z-axis. A point in space is identified by all 3 coordinates. To plot the point XYZ, go X units along the X-axis, then Y units in the direction of the Y-axis, then Z units in the direction of the Z-axis. Okay, you have the XY plane, which is what we are familiar with. Then we also have the XZ plane and the YZ plane. In 2 dimensions, the coordinate axis partition the plane into 4 quadrants. Similarly, the coordinate plane divide the space between them into 8 regions about the origin, called octants. The octants fill R cubed in the same way that quadrants fill R squared. Most work in 3-dimensional space is comfortable extension of the corresponding concepts in 2 dimension. In this section, we use our knowledge of circles to describe spheres. Then we expand our understanding of vectors to 3 dimensions. To accomplish these goals, we begin by adapting the distance formula to the 3-dimensional space. So d is the difference in x squared, difference in y squared, difference in z squared. Add them together and find the square root. Find the distance between point 3 minus 1, 5 into 1 minus 1. So 3 minus 2 is 1. Hold on. 3 minus 2 is 1. And then minus 1 is minus 2. Minus 2 squared is 4. And then 5 minus 1 is 6. Then we have 6 squared. And we get 6.403. Yeah. Before moving on to the next section, let's get a feel for how R cube differs from R square. In R square, lines that are not parallel must always intersect. This is not the case in R cube. For example, consider the lines shown in 2.3. These two lines are not parallel, nor do they intersect. You can also have circles that are interconnected but have no points in common. Writing equations in R cubed. Now that we can represent points in space and find the distance between them, we can learn how to write equations of geometric objects such as lines, planes, and curved surfaces in R cubed. First, we start with a simple equation. Compare the graph of the equation x is equal to 0 in R squared and R cubed. Okay, so x is 0 is this line. X is equal to 0 is the entire plane. In space, the equation x is equal to 0 describes all points 0 by z. Okay, writing equations of planes parallel to the coordinate planes. Write an equation of the plane passing through the point 3, 11, 7 that is parallel to the yz plane. Find an equation of the plane passing through the point 6, minus 2, 9 and 0, minus 2, 4. Wait. Does Desmos have a 3D? So write an equation of a plane passing through the point 3, 11, 7 that is parallel to the yz plane. I guess that would be just be x is equal to 3, right? Can be represented, yeah. Find the equation of the plane passing through the point 6, minus 2, 9 and 0, minus 2, 4 and 1, minus 2, negative 3. They all have negative 2 at y in common. So wait. You have x, y. Yeah, they all have -2 in common. So it's a plane that's at -2. Yeah. Y is equal to -2. Oh, sorry, this is z. I mean here. Can I make it translucent? I don't think so. Yep. As we have seen in R squared, the equation x is equal to 5 describes the vertical line passing through the point 50. This line is parallel to the y-axis. In a natural extension, the equation x is equal to 5 in R cube describes the plane passing through the point 500, which is parallel to the yz plane. A sphere is a set of points in space equidistant from a fixed point. The center of the sphere, just as a set of all points in a plane that are equidistant from the center, represents a circle. In a sphere, just as in a circle, the distance from the center to a point on the sphere is called the radius. Okay, so you have a standard equation of a sphere, x minus a, y minus b, and z minus c squared. ABC is the center, and adding them all up gives r squared. Find the standard equation of the sphere with the center 10, 7, 4 and point -1, 3, -2 are shown in this figure. So what did they mean? Oh, we just find the radius by subtracting each point. So 10 minus -1, 10 minus -1 squared, 9 squared, 7 minus 3 is 4 squared. Then 4 minus -2, 6, and then we have 6 squared. So 11.5325. This is the length of the radius. So basically x minus 10 squared plus y minus 7 squared plus z minus 4 squared is equal to 11. Where was the, we remove the square root. It's equal to 133. It says 173. I did 10 minus -1, right? Should be 11, not 9. Finding the equation of a sphere, let P and Q and suppose line segment PQ forms the diameter of a sphere. Find the equation of a sphere. So this forms the diameter. I think we find the average point. So -5 plus 3 divided by 2. -5 plus 3, all that divided by 2 is -1. Two plus 4. And then we have 3 minus 1. -1, 3, 1. Does it make sense? So x is -1. Then y is 3. Then z is 1. Yeah, I guess that makes sense. That's the radius, right? That's actually the center. So we have the values for ABC. We have the values for these. It's negative 1, 3, and 1. And then if we want the radius, we can do minus 5. Yeah, we have to subtract values from this with the radius. But I don't want to do that. But you get the point. Yeah, negative 1, 3, and 1. The radius they calculated is root 21. Um, Describe the set of points in three-dimensional space that satisfies this equation. Okay. Working with vectors in R cube. Just like two-dimensional vectors, three-dimensional vectors are quantities with both magnitude and direction, and they're represented by directed line segments. The three-dimensional vector, we use three-dimensional arrows. So the zero vector is 0, 0, 0. Three-dimensional vector 2, 4, 1 is represented here. Of course, the previous properties still apply, so we can multiply them with a scalar and we can add and subtract them. Also, there's a third dimensions k. So I, j, k. Let pq be the vector with initial point p. So 3, 12, 6. And terminal point q, minus 4, negative 3, and 2, as shown. Express pq in both component form and using standard unit vector. So if I want to do this, hold on. Can I is there a shortcut for clearing all this? So I would do 3 minus 4, which is just plus 4, 7. 12 minus 3, which is just 15. Then 6 minus 2 is 4. You have 4. So 7, 15, 4. I think that's the component form. PQ. Wait, shouldn't it be opposite? I did 3 minus 4, right? No, it should be minus 7 minus 15 minus 4. And we can represent them with ijk. Let me see. Yeah, it's going downwards. As described earlier, vectors in three dimension behaves in the same way as vectors in a plane. The geometric interpretation of vector addition, for example, is the same in both two and three dimensional space. Let V be minus 2, 9, 5 and W be 1, minus 1, 0. Find the following vectors. So they have 3V minus 2. Hold on. Let's just write it down. If I take picture, would it cause an error again? Copy. No, it worked this time. V is equal to and then W, I'll just write it like this. 1, -1 and 0. And then 3V is -6, 27 and 15. And then -2W is -2 to 0. So adding these two together, we get -6 plus -2, which is -8. 27 plus 2 is 29. 15 plus 0 is just 15. And then 5 times the magnitude of W. So the magnitude of W is 1 square plus 1 square plus 0 square, which is √2, right? And then 5 times this would just be 5√2. And then if we have 5W, we have 5 minus 5, 0. Shouldn't it be the same? Five square plus 5 square plus 0. 25 plus 25 is 50. Is this correct? $50. Oh yeah, √50 is 5√2. Then lastly, we had to find the unit vector. A quarterback is standing on the football field preparing to throw a pass. His receiver is standing 20 yards down the field and 15 yards to the quarterback's left. The quarterback throws the ball at the velocity 60 miles per hour towards the receiver at an upward angle of 30 degrees. Write the initial velocity vector of the ball v in component form. Hold on. So the direction the ball is going. So it's 20 in one direction, 15 in another perpendicular direction, and then I guess sine 30. But the thing is, 15 bar, the quarterback throws the ball at the velocity of 60 miles per hour. Write the initial velocity vector of the ball v. So 60 miles per hour over here. And then in this direction, it's 60 cos 30. And in the upward direction, it's 60 sine 30. But they want it in component form. I think we are supposed to find this angle. Then we have 60 sine 30 over here. And then we are supposed to find the velocity in this angle and this angle. Wait, hold on. Okay. So basically we have this. $15, $20, and then this, let's call it theta. Let's do it in degrees. So we have tan, and then 15 over 20. Yeah, 36.87. And then we have 30 degrees. We have theta. This here is you have 60 miles per hour. And then this here is 60 sine 30. And then this here is 60, 30 degrees, 60 sine 30. And then this here is 60 cos 30. We got the z direction. Now we need the x and the y direction. So since this is 60 cos 30, then in the x direction, this would be sine theta. Wait. If I do this, theta 60 cos 30, and we want to find this, then we have 60 cos 30, which is the hypotenuse, times it by sine theta. Then 60 cos 30 times it by cos theta. So then the velocity, initial velocity v, V is theta. Let's do this. And then 60 cos 30 cos theta I 41.57. And instead of cos, we do sine. 31.18. And then lastly, we do 60 sine theta, sine 30. Which is just 30. Write the initial velocity vector be in the component form. You get 30, 24 root 3, and 18 root 3. What's 24 root 3? 24 root 3. Is this what I got? Yes. And then 18 root 3. Yeah. Okay, I will end the stream here then. And next stream I might do C++ or I will continue studying vectors. I don't know. I'll see. Anyways, see you next time, I guess.